1 plus 2 plus 3, continuing all the way to 100, equals 5050. The answer looks far too precise to guess and far too large to see at a glance. Yet the entire sum can be finished with one multiplication and one division. The trick is not faster arithmetic, it is a change of shape. We will pair opposite ends, build two identical staircases, and watch a rectangle appear. Then the same construction will explain triangular numbers, handshakes, and every arithmetic series. This is symmetry. Let's find out why. First, see why ordinary addition hides the structure we need. Write the integers from 1 through 100 in a row. Adding from the left creates a running total: 1, 3, 6, 10, 15, 21. The totals grow, but every step depends on the previous one, so the full pattern remains hidden inside 99 separate additions. A calculator can execute those additions quickly, yet speed does not explain why the final answer is 5050. To understand the answer, we need a view in which all 100 terms participate at once. The important clue is that the list has two ends, and the ends fit together unusually well. Represent each number as a row of dots. 1 dot, then 2, then 3, continuing upward. The first few rows form a staircase whose total number of dots equals the sum. Extending this picture to 100 rows creates a triangular array. Now the problem has become geometric. We are no longer asking how to perform many additions. We are asking how to count one shape. The sloping edge records the increasing terms, the base contains 100 dots, and the height contains 100 rows. But a triangle is awkward to count directly because its rows have different lengths. Small cases reveal the sequence. One row contains 1 dot. 2 rows contain 3. 3 rows contain 6. 4 rows contain 10. 5 rows contain 15. These are called triangular numbers because each total packs into a triangle. The differences between successive totals are exactly the counting numbers we started with. That observation works in both directions. Adding the next row grows the triangle, while removing the bottom row returns the previous total. It gives a recurrence, but still not a direct formula. We need a way to replace unequal row lengths with equal ones. Now let the first and last terms solve each other. Call the unknown sum S and write it forward. 1 plus 2 plus 3 through 98, 99, 100. Directly beneath it, write the same sum backward. 100 plus 99 plus 98 through 3, 2, 1. Add vertically. The first column is 1 plus 100, the second is 2 plus 99, and every column equals 101. Nothing has been approximated or rearranged illegally. We have written two copies of the same sum in opposite orders so that their complementary structure becomes visible. There are 100 columns, and each column sums to 101. Therefore, 2s equals 100 times 101, or 10,100. Divide both sides by 2, and s equals 5050. The arithmetic takes seconds once the pairing is visible. Notice what created the factors. 100 counts the number of terms, and 101 is the common pair sum. Dividing by 2 removes the duplicate copy. So the answer is not a memorized coincidence. It is half of a rectangle whose width is the number of terms and whose height is first plus last. The same idea works without 100 terms. For 1 through n, write the list forward and backward. Every vertical pair becomes n plus 1, first plus last, second plus second last, and so on. There are n positions, so 2 copies of the sum equal n times an plus 1. Dividing by 2 gives the general formula. 1 plus 2 through n equals n times n plus 1 over 2. The letters merely record the same construction. 100 is not special. It is one input to a rule that works for every positive integer. The algebraic pairing has an exact geometric twin. Return to the dot staircase with rows 1 through n. Make an identical copy, rotate it 180 degrees, and slide it against the original. Every short row meets a long row. The row of 1 meets the row of n, the row of 2 meets n minus 1, and each combined row has n plus 1 dots. The jagged boundaries disappear. Together, the two staircases fill a perfect rectangle with n rows and n plus 1 columns. This is the same forward and backward argument, now visible as a transformation of area. The rectangle contains n times n plus 1 dots. Because it consists of two congruent staircases, one staircase contains exactly half that number. This gives n times n plus 1 divided by 2 again. The division by 2 is no longer an algebraic instruction. It means taking one of two equal pieces. For en equal to 100, the doubled array is a rectangle 100 rows high and 101 columns wide. Its 10,100 dots split evenly into two staircases of 5,050. This picture also handles odd and even n without separate tricks. If n is even, n divided by 2 is an integer, so we may halve the number of rows and multiply by n plus 1. If n is odd, n plus 1 is even, so we halve the number of columns instead. One of two consecutive integers is always even. That is why n times n plus 1 can always be divided by 2 with no remainder. The geometric rectangle makes the integrality obvious. A whole number of dots cannot produce half a dot. A numerical table makes the rectangle rule easy to audit. For n equal to 6, the formula gives 6 times 7 divided by 2, or 21. Counting the rows directly gives 1 plus 2, plus 3 plus 4, plus 5 plus 6, also 21. For an equal to 7, the formula gives 7 times 8 divided by 2, or 28. The new triangle is exactly the old 21-dot triangle plus a bottom row of 7. The formula therefore passes both a direct count and a one-step growth check. These checks matter because a visual rearrangement should agree with the arithmetic at every scale, not only for the dramatic case of 100. Now read everything the rectangle tells us about the sequence. Define t sub n as the nth triangular number. The construction proves t sub n equals n times n plus 1 over 2. Substitute n equals 5 and obtain 5 times 6 over 2, which is 15. Substitute n equals 10 and obtain 10 times 11 over 2, which is 55. Substitute 100 and recover 5,050. A direct formula lets us jump to any triangle without building every earlier one. For 1,000 rows, the answer is 1,000 times 1,001 over 2, or 500,500. The formula agrees with the recurrence. Add the next row, n plus 1, to t sub n. Algebra gives n times n plus 1 over 2, plus n plus 1. Factor n plus 1, leaving n over 2 plus 1, and simplify to n plus 1 times n plus 2 over 2. That is exactly t sub n plus 1. So the closed formula and the staircase growth rule describe the same object from two directions. One tells us how to build the next triangle, the other counts the completed triangle immediately. A second check uses consecutive triangular numbers. Place t sub n and t sub n minus 1 together along their sloping edges. The two triangles form an n by n square because their rows complement to n. Algebra confirms it. N times n plus 1 over 2 plus n minus 1 times n over 2 equals n squared. For n equal to 5, 15 plus 10 equals 25. This identity connects triangles and squares and shows that the pairing idea keeps producing new shapes, rather than a single isolated formula. The same triangle counts relationships, not just dots. Imagine n plus 1 people, and suppose every pair shakes hands once. The first person can shake with n others. After those are counted, the second has n minus 1 new handshakes, then n minus 2, continuing down to 1. The total is n plus n minus 1 through 1, which is t sub n. With 101 people, the number of handshakes is 100 plus 99 through 1, 5,050. The same staircase appears because choosing an unordered pair naturally produces descending row lengths. Combinations express the same count compactly. The number of ways to choose two objects from n plus 1 is written, n plus 1 choose 2. The formula is n plus 1 factorial divided by 2 factorial times n minus 1 factorial. Cancelling the common factorial leaves n times n plus 1 divided by 2. Therefore, t sub n equals n plus 1 choose 2. A triangular number counts every pair among n plus 1 objects. The dot triangle, Gauss's sum, the rectangle, and the handshake graph are 4 representations of one counting structure. This interpretation explains why triangular numbers appear in tournament schedules, network links, line segments between points, and comparison tests. Whenever every object must meet every later object exactly once, the counts descend by 1, n minus 1, down to 1. The order may look different, but the staircase is identical, recognizing that structure prevents double counting. Counting both A with B and B with A builds the doubled rectangle, dividing by 2 returns the unordered pairs. Gauss's reversal is therefore a general method for removing symmetry duplicates. There is another safeguard against double counting. Start with n plus 1 objects and draw an arrow from every object to every different object. This ordered network has n plus 1 times n arrows. Now erase each arrowhead and merge every opposite pair of arrows into one undirected edge. The count is divided by 2, producing n times n plus 1 over 2. This construction explains the denominator independently of dots or algebra. 2 directions describe one relationship. It also shows exactly when the triangular formula should not be used. If direction matters, as in who sends a message to whom, keep the doubled count. If direction does not matter, as in a handshake, halve it. Finally, extend the pairing method to every evenly spaced list. Consider an arithmetic sequence with first term A, last term L, and n terms. Write it forward and backward. Every aligned pair equals a plus L, regardless of the common difference. There are n pairs across the doubled sum, so twice the sum equals n times a plus L. Divide by 2. The sum equals n times the average of the first and last terms. Consecutive integers are merely the case A equals 1 and L equals n. The real principle is that symmetric positions in an arithmetic sequence share one constant average. Test the rule on 3 plus 7 plus 11 through 43. The common difference is 4. To find the term count, subtract first from last, divide by 4, and add 1. 43 minus 3 over 4 plus 1 equals 11. The average of the endpoints is 23. 11 terms times 23 gives 253. Pairing confirms it. 3 plus 43, 7 plus 39, and every opposite pair totals 46. The unpaired middle term is 23, exactly half a pair. The formula handles odd term counts automatically. The deepest lesson is not the number 5050. It is the move that produced it. When a long calculation has opposite ends, reverse a copy and look for invariance. When unequal rows form a staircase, duplicate and rearrange them into a rectangle. When relationships are counted twice, divide by the symmetry. These are different languages for one idea. Reorganize before calculating. Gauss's sum is memorable because one elementary change of viewpoint turns 100 additions into a visible object whose count is unavoidable. 100 terms became one rectangle, and 5050 became completely and visually inevitable. If you enjoy seeing formulas built rather than memorized, subscribe to Symmetry. Thank you for watching.